to clear the calculator. So we start with the blue button, second, and then a plus sign, and then 7, 1, 2. So second plus 7, 1, 2 will clear your calculator. And this is going to be pretty familiar. This is mostly a review from Math 3, but it's got one thing that is going to be new to us that we didn't learn in Math 3. So the first thing we're going to do is just graph the parent function for a parabola or a quadratic, y equals x squared. So to graph that on here, I'm going to hit the y equals button. And then I have to type x squared, so the x button, x, and then the squared is right down here, x squared. And then how do we get to the table so that we can see the x and the y values? So over here is how we graph it. If you just hit graph, you'll be able to see it. And then right above that in blue, it says table. So if you hit second graph, then you can see x and y coordinates. X and y coordinates. Okay. So the middle is 0, 0. A couple points to the left of that, negative 1, 1, which makes sense if you plug in negative 1. Negative 1 squared would be negative 1 times itself. That just gives you 1. Negative 2 is 4. Negative 2 times itself is 4. 1 times itself is 1. 2 times itself is 4. So those are the points for the parent graph. If we need more points, negative 3 squared is 9, positive 3 squared is positive 9. And we can graph those on this particular coordinate axis because it's big enough to do those points. But typically, we're only going to use the 5 that are in this table. So 2, 4, negative 2, 4. So that's enough points, but if you want to do 3, 9 and negative 3, 9, just because our graph is big enough, you can do that. And parabolas are U-shaped graphs, so we want to make sure that this looks like a U when we draw it, not a V. Anyone remember what function is a V-shaped graph? What type of function makes a V? Absolute value makes a V-shaped graph. So the U-shaped graph are called quadratics, or the shape is called a parabola. Parabola. So some of these transformations over here, this is the transform graph. This is what it looks like. Most of them are going to be familiar. One of them is new in Math 4. So if you have a coefficient in the front of the parentheses, if that number is negative, then that means that the graph has reflected over the x-axis. If that number is greater than 1, it doesn't matter if it's positive, doesn't matter if it's negative, but if that number is bigger than 1, then that means it's a vertical stretch. If that number is smaller than 1, then it means it's a vertical compression. So vertical stretch means tall and skinny. Vertical compression means short and fat. So you either vertically stretched it or you vertically compressed it like vertical squish. Inside the parentheses, we have x minus h. This is the graph moving to the left or the right, and it's always the opposite of what you would think. A positive number moves it to the left, a negative number moves it to the right. And then the number on the end tells you if the graph has shifted up or down. And this is exactly what you would think. A positive number moves it up, a negative number moves it down. And then we have the one that is new to us that we did not learn about in Math 3, and that is the b value. So it's a coefficient, but it's a coefficient for x inside the parentheses. So before we had a coefficient, but it was outside the parentheses. It happened to whatever happened to be squared. So you did the operations first and then you did that coefficient. This is happening to the stuff before it's being squared. Do you guys see the difference? Coefficient, but it's inside the parentheses. It's before the squared happens. And this one, if it's negative, this one is a reflection over the y-axis. It reflects the graph over the y-axis. This one is similar to the idea of left and right, where if it's a positive number, it moves to the left. If it's a negative number, it moves to the right. It does the opposite of what we're used to it doing. So if the b value is a number that is greater than 1, we are used to that being like a stretch. So in this case, it would be a compression. Now, this is not a vertical stretch or a vertical compression. It is a horizontal. So anything that goes on inside the parentheses, it's a left-right movement. That's something that happens left and right. That's a horizontal movement. So it has to do with horizontal stretching as well. So what we're learning now is that the stuff that happens inside happens to the x-coordinate, happens left and right. The stuff that is on the outside happens to the y-coordinate and happens up and down. You guys see the difference? So one thing goes vertically, one thing goes horizontally. So if the b value is greater than 1, it's going to be the opposite of what we would think. It's going to be a horizontal compression. So the sign doesn't matter because the sign has to do with a reflection over the y-axis. It's the size of the number that matters. If the b value is less than 1, again, not talking about the sign here, we're just talking about the size of the number. If the size of the number is less than 1, it's a horizontal stretch. So what this means now for Math 4 is that we have to look inside the parentheses and we have to make sure that the inside of the parentheses have been factored, that a GCF has been taken out of the inside of the parentheses before we determine if there is a left-right shift. Because if we decide if there's a left-right shift before we factor inside the parentheses, then our answer for the left-right shift could be incorrect. Okay? So let's look at example 1. The incorrect transformation for this would be right 6. That would be incorrect because negative 3x minus 6 can be factored. The inside of these parentheses can be factored. Everyone see how that would work? So let's go ahead and take this function. Let's rewrite it. So we're going to have y equals, I've got my big set of parentheses, but I need to factor inside. So what can I factor out? A negative 3 is what can be factored out. And when I factor out the negative 3, what is left over? Plus 2, x plus 2. So the graph did not shift to the right 6. What did the graph actually do? It shifted to the left 2. Do you guys see how that could mess you up if you didn't factor it? Okay, so this graph shifted left 2. Okay, we still have a plus 3 on the end. What does the plus 3 on the end tell us? Up 3. Okay, so that transformation is still just as simple as it ever was. The end number doesn't get changed at all. In here we have a coefficient, but it's inside the function. So if we have a negative in the front inside the function, what does that mean? Reflect over y. This has been reflected over the y-axis. So we're going to say reflect over y. All right, and then it's got a 3, which feels like it should be a stretch, but it's not a stretch because it's on the inside of the function. So what is that instead? Horizontal compression. All right. How are your brains feeling? Good? Okay. So what we're going to do is we're going to write the vertex. Can somebody tell me what the vertex is? Don't look at the original, look at the one that we fixed. You're close with the 2, 3. Negative 2, 3. Okay, so I'm going to go left, 1, 2, up, 1, 2, 3, 1, 2, 3. But this vertex has been reflected over the y-axis. So where would the vertex actually be? On the other side, positive 2, 3. Okay, so what we're going to do is we're going to look for this. We're going to graph this on the calculator, and we're going to look for that vertex. So we've got, and you can type in, what I would do is probably type in the original function, first off, because it's easier, and second off, we just want to make sure we didn't make any mistakes here. So negative 3x minus 6. And then to be able to look at the values on the table, I'm going to hit second graph to look at the table values. So negative 2, 3 is not a point on the graph, but positive 2, negative 3x minus 6. Oh, plus 3 on the end. Thank you. Plus 3. Sorry, negative 2, 3. Oh, we already reflected it over because it looked like it was right 6, so we already reflected it over. Sorry, my bad. I just had to think about that for a second. The vertex is negative 2, 3. It looked like it was moving to the right, but we reflected it over, so it is moving to the left. That was my bad, you guys. Sorry. Okay, so we find the vertex on here, and then once you find the vertex, now graph a couple points to the left, a couple points to the right. And that's how you can make sure that you've graphed everything that you need to. So here, this graph is so stretched out that we can't get very much on it. We can't do 2 points to the left and 2 points to the right, but we can at least do 1 point to the left and 1 point to the right, even though it's off the graph. 12 isn't too bad as far as being off the graph. So we're going to do negative 3, 12 and negative 1, 12. Negative 3, 11, 12, negative 1, 11, 12. There we go. And it's just a really... Now, why would this graph be skinny? Can somebody make this make sense for me? So if we think about what transformations we had, why would it make sense for that graph to be really skinny based on the transformations we had? It's this one right here. What does that mean? So if the normal U was this wide and you compress it, what are you doing? You're squishing it. So if you horizontally compress a graph, you are squishing it and making it skinnier. So a horizontal compression is going to be really similar to doing what to a graph? What is it going to be similar to doing vertically? It's going to look like when you vertically stretch it. Does that make sense? So vertically stretching a graph makes it look tall and skinny, but the same thing happens if you take a graph that's this wide and you push it together, it's going to squish it. It's also going to make it look tall and skinny. Does that kind of make sense? Okay. Which, if you think about it, feels pretty logical because it's a big number. It's a number bigger than 1 that's kind of sitting in the front. So it should act kind of the same way, even though we would manipulate the math a little bit differently. Okay? All right, let's try the next one. So the next one is asking us to do something similar, but it gives us slightly different numbers, and it's an inequality. If it's an inequality, what do we have to keep track of when we graph this? How does it graph differently if it's an inequality versus an equation? Yeah, we have to figure out some shading, right? Is the line automatically solid? No, it could be dotted. We have to figure it out based on the symbol. Okay, so let's look at this. Is the inside of the parentheses ready to go? Is this ready to go? No. How do you know it's not ready to go? There's a number in the front. So the X has a number in front of it. The only way the parentheses would be ready to go is if the X is alone. So since the X has a number in front of it, that means that we can factor what's inside the parentheses. So we're going to have to take out the number in front of the X. We're going to have to factor out the 1/2. So how many 1/2s go into 2? 4. 4 1/2s go into 2. All right, and let's just make sure that we all know how to double check that on our calculator. If you wanted to see how many 1/2s go into 2, you cannot do 2 divided by 1/2. If you type it in like this, your calculator is going to give you the wrong answer. You can do 2 divided by 1/2, like that. For how many 1/2s go into 2, that would be correct. You could type it in like a fraction. To type fractions on your calculator, you do alpha, the green button, alpha y equals. And then you could do 2 divided by 1/2. Does that make sense? 2 divided by 1/2. Okay, so there are 4 1/2s in the whole number 2. So at this point, what transformations do we see? Say it again. Down 5. What else do we see? You're close. Left 4. Okay. Okay, the negative in the front is reflect over X. Horizontal stretch. So because of that 1/2, we're taking a graph that is this wide, and we're going to be stretching it, which is going to look the same as a vertical compression. It's going to look the same. Okay, so can you guys tell me what the vertex is? -4, -5. So we're going to go left 4, down 5. And then, so you look at this number and you do the opposite, because whatever, if you've noticed, whatever's inside, you always do the opposite of what it looks like. So if it looks like it's right, it's actually left. If it looks like it's a compression, it's actually a stretch. If it looks like a +4, it's actually a -4. So you just do the opposite. And then the number on the end is a -5, so we're actually going to use the -5. So anything that's on the outside is exactly what it looks like it should be. Yeah. Okay, so -4, -5. So I'm going to graph this in my calculator. Negative, and then I'm just going to type it in the way that it was to start with. And I'm keeping in mind that when I read this out loud, this is negative, and this is a minus. So negative, and then 1/2 x plus 2 squared minus 5. And so on my calculator, this down here is the negative button, and this over here is the minus button. So your calculator, the graphing calculators do differentiate between those two, whereas Desmos does not. Desmos lets you use the same thing the whole way through. But your graphing calculator needs you to make a difference. So from here, we can look at the table, and we'll just find the vertex on the table, and then we'll look for 2 points on each side. So to get to the table, we're going to hit second graph, and I'm going to be looking for the point -4, -5, and then doing 2 points on either side. If you want to skip the decimals, you can, and you can just look for the 2 whole number points on each side. That would be fine. So -4, -5, and then I've got -6, -6. And -2, -6. And then the next whole number is -8, -9. And then I think it was 0, -9. Yeah. And there's my graph. It's been horizontally stretched out to look wider. Okay. How do your brains feel about finding those transformations? Okay. So we'll practice finding the transformations on some more in the rest of the notes too. Oh, yeah, we got a shade. Was it correct of me to do a solid line for that one? Did I do that correctly? Yes. So just a reminder, let's write this off to the side. If we have less than or equal to or greater than or equal to, that's a solid line. If we do less than or greater than, that's a dotted line. And then if we are dealing with a linear equation or a linear inequality, we would say like, okay, you either shade above the line or below the line, or you would either shade to the left side of the line or the right side of the line, because that's how lines divide a graph. There's only one side or the other. With a parabola, you don't have a left side versus a right side. You have the inside of the parabola versus the outside of the parabola. Those are like the two sides that you have. So we need to pick a point to plug into the parabola, and then we're going, or the quadratic, and then we're going to see if that point is true, because you always do the shading where it's true. So what point would you guys like to plug in? It can be any point, it just has to not be on the curve. What point would you guys like to plug in? 0, 0. And a lot of people choose 0, 0 because it's easy to plug in. 0 is the easiest number as far as multiplying it by something or adding it to something. So 0 is outside of the parabola. So we're going to plug it in and just see if it works. So 0 for x, 0 for y. And we're going to have 0 is less than or equal to negative of 1/2 times 0 plus 2 squared minus 5. So, yeah, 1/2 times 0, yeah. And then if you want to get out of this window, you can just hit second, and then right above that says quit. The mode button says quit, so second quit will get you out of that window. So I've got negative 1/2 times 0 plus 2 squared minus 5. And that should be -9, I think. Yeah, because we got one of those points. We graphed one of those points. So negative 9. 0 is less than or equal to negative 9. Is that true or false? False. 0 is not less than a negative number. So if 0, 0 is false, that means that all of the points that are outside the parabola are false. Which means where should the true points be? On the inside of the parabola. This is where the true points should be. And we shade where things are true. So we're going to shade inside the parabola. All right, go ahead and turn the page. So I left all these definitions in here. These are all things that you guys learned in Math 3. I just want to make sure. So we're going to go through this like real quickly because this should be review. So if you look at example 3, what's the vertex? Negative 5, negative 6. Okay. For the domain, we look at the graph from left to right, and we just see how far does the graph go to the left, how far does it go to the right, does it skip anything? So what do you notice about the graph from the left to the right? It's infinity. So if we look at the left, we have an arrow that goes left forever. That's negative infinity. If we look to the right, we can see that we have an arrow that goes to the right forever. That's a positive infinity. And then if we're doing this interval notation, what do we always put around our infinities? Do we put brackets or do we put parentheses? Parentheses. Okay. Use a bracket for a number that actually shows up. So these arrows, even though they go left and right forever, if you said, Miss Rice, is this actually where negative infinity is? I'd say like, well, no, because that arrow is technically at negative 8. So since it's not a number, since negative infinity is not a number, I can actually show you like that's where it is, that's where it's happening. That's why you put a parenthesis there, because it's not actually there. Yeah. All right, the range is the y values. So domain is the x values, the range is the y values. So those are the numbers from the bottom of the graph to the top of the graph. So what's the lowest number at the bottom of the graph? Negative 6. So it goes down to negative 6 at the bottom. And then how high does it go at the very top? Infinity. So infinity we cannot touch. But down here, is my pencil touching negative 6? Yes. So that gets a bracket. All right, this part of the notes is ugly because I forgot to go back and make the table disappear, so apologies for that. This example, we need to rewrite the equation before we can find the vertex. I'm going to have you guys find it anyway. So if we rewrite this so that we can find the vertex, that would make our equation what? What would the equation be? You're close. So take the negative 1 out. Change the sign, yeah. So it'd be x minus 5 when we take the negative 1 out. And then we've got the squared. So what are the transformations for this graph? Right 5. So 1 is normal. 1 is not a stretch, not a compression. That's normal. but it is negative. What's the negative? Reflect over the y-axis. Because we had a negative and we pulled it out.
Is it right? Oh, I did that.
So we had a negative and we pulled it out, and that took the negative and it made it or it took the positive and it made it a negative. Change the sign. Yeah. What's the 3/2 mean? It's in the very front. Vertical stretch. Okay. So it's been shifted to the right 5, it's been reflected over y, and it has a vertical stretch. What's the vertex? 5, 0. Yeah, you can see that on the graph, but you can also see it from the equation. Positive 5, and then there's nothing on the end, so it'd be 5, 0. Okay. So increasing and decreasing intervals are just where the graph slants up to the right or slants down to the right. So if you have me as a Math 3 teacher, I always put a little stick figure here, and I make the stick figure go for a walk. So if the stick figure started walking, is the stick figure walking uphill or downhill? Downhill. So this is decreasing. And then the stick figure gets to the vertex. And then the stick figure starts walking over here, and is this uphill or downhill? Uphill, so the stick figure is increasing. Okay, so right here is the vertex. What is the x value for the vertex? 5, okay. What is the x value for a left arrow? What number do we put for a left arrow? Negative infinity. What number do we put for a right arrow? Infinity. Okay, so the increasing interval, we put the numbers that are on either side of the word increasing. So the word increasing is right here. The numbers on either side are 5 and infinity. So that's the answer for increasing interval. Now, infinity always gets a parenthesis because you can never touch that. Okay, now 5 only gets a bracket if the stick figure is actively walking uphill at that number. If you can look at that number and say, yes, the stick figure is walking uphill at that exact moment. So if we look at the bottom right here where the vertex is, if you look at the vertex, is the stick figure walking uphill right here? No. Okay, so I'm going to put a parenthesis there. For the decreasing interval, I look at the word decreasing, I look at the numbers on either side, and I write them down. Negative infinity and then 5. Infinity always gets a parenthesis. That's never a number I can put my finger on. We've never seen a graph that goes to infinity. Does that make sense? Even with Desmos, if you kept pulling the graph, if you kept pulling it over, pulling it over, pulling it over, pulling it over, so you could get bigger and bigger numbers, does it ever go to infinity? No. So you're always going to have a parenthesis around your infinity because no matter how big you make your graph, you're never going to get there. Okay? Now, if we look at the 5, is my stick figure walking downhill when he is standing right here? No. So that's going to be a parenthesis. Okay. So what we just figured out is that, we're going to put this on our notes, domain is an x value, range is a y value, increasing and decreasing are both x values. So that is something to keep in mind because that usually messes students up, is they're never sure when to use the y coordinate, when to use the x coordinate. So far, the only thing that uses a y coordinate is the range. Everything else uses x coordinates. Okay? All right, maximum and minimum. We have the location of the highest value of the function or the location of the lowest value of the function. We typically write it as a point. There's one other way they can ask about this, so we're going to write this real big. If they ask it as a where question, they actually want the x coordinate. If they say where is the maximum or where is the minimum, they want just the x coordinate. If they say what is the maximum or what is the minimum, they want just the y coordinate. But when I write it like this, tell me the maximum, tell me the minimum, then go ahead and just give me the x and the y coordinate together. Okay? All right. So here, if we want to figure out what the maximum or minimum is, it's going to be for a parabola, for a quadratic function, it's going to be the vertex, and there are not both of them. It's just one or the other. So with this graph, for maximum, we're going to say none. And then for minimum, we actually have an answer, but we have to fix this so we can see what the answer is. I don't want to even read this graph. I have to squint too much to do that. So how can we fix this equation? The GCF is -2. So I've got -2 squared plus 1. And then what would be in the parentheses? X plus, x plus 5, because we took out a negative. And so what is the vertex? -5, 1. And that fits our graph. -5, 1 makes sense for that. So the minimum is -5, 1. Okay, and let's go ahead and practice the transformations for this one. So can somebody tell me what some of the transformations are? We got up 1, left 5, good. Reflect over y. Horizontal compression, because it feels like it should be a stretch, and so it's the opposite. So whatever's inside the parentheses is always the opposite of what you should think it is. Okay, let's go back up to example 3. This one right here, we didn't write the transformations for this one, so let's do that one. What are the transformations up here? Down 6. Left 5. Vertical stretch. Okay. All right, go ahead and flip the page. X-intercept and Y-intercept. When you guys did this last year in Math 3, did you use a calculator or did you use Desmos? Desmos, wonderful. We're going to use a graphing calculator. Okay, put the calculator in front of you. We're going to go to Y equals and clear what is in there currently. So while it's hovering over the negative, go ahead and press the clear button. We have to type the square root of 2. Anyone know how to type the square root of 2? Second, x squared. Yeah, so if you look at the x squared button, right above that is the square root sign. So we're going to do second x squared. There's your square root 2. And then I'm going to get out of that. And then I'm going to type x minus 1 squared. X minus 1 squared minus 8. And then you can go ahead and hit graph. Just want to make sure it looks the same as the graph that's on your paper. Okay, everyone got it graphed? Yes? Okay. So the way that you use these calculators to calculate different things for you is this next button over here. Above it, you can see in blue it says calculate. So we're going to hit second trace. Second trace. And that brings you to a menu of different things you can calculate. So another word for x-intercept is the 0 of the function, because when you find the x-intercept, the y value is 0, and y equals the function. So a lot of times they call the y the function. Y equals the function, so they say the function. So the 0 of the function is another way to say x-intercept. And so what we just did is we did second trace. And in that menu, we're going to use option number 2. So second trace, option number 2. So you can either type a number 2 to get to it, or you can use your down arrow to get to it and then press enter. It doesn't matter, okay? So I'm going to press enter. Now, my first x-intercept I can see is between -2 and -1. And your calculator is asking you where to look for that answer. So it says left bound and right bound. And so what you're going to do is you're going to tell your calculator, I think the answer is in between these two numbers. So you can be really accurate when you're telling your calculator where to look, or you can be really lazy when you're telling your calculator where to look. It doesn't matter, your calculator will do just fine. So I like to be lazy, so when my answer is over here, on the left side of the graph, I tell my calculator to look between -10 and 0. That's just me, because that's the left side of the screen. If you're not being lazy, you might tell your calculator to look between -2 and -1, because that is really, truly where the x-intercept is. You guys see the difference? So I like to be lazy because I never want to have to squint my eyes and look and see exactly where it is. I don't like to think about it. I just say, oh, it's on the left side. It's between -10 and 0 somewhere, okay? So for left bound, I'm going to start typing -10. So -10, and when I typed it, it showed up there for left bound. Now, when I press enter, it's going to ask me, okay, what's to the right of the answer? So now I'm going to press 0. And then I'm going to press enter again. It's going to make a guess where the answer is. The guess is going to be stupid. Never listen to the guess. Press enter one more time, and it's going to find the x-intercept for you. Ms. Rice, that's harder than Desmos. Why aren't we using Desmos? Because from after Math 3, anytime after Math 3, you can't use Desmos because it's an internet-based calculator. So if you get to college and you're in a math class and you say, hey, professor, can I use Desmos? Your professor's going to say, ha, 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 no. Why did you ask me that? That's internet, okay? Can you use these? Absolutely, okay? For any test from now on, these are the only thing you're going to be able to use. If you went to any high school besides this one, you wouldn't have been able to use Desmos anyway, all right? The only reason you guys have been allowed to use it is because of GoGuardian, and most high schools don't have that, all right? So first x-intercept is -1.378. So let's write that one down. -1.378 comma 0, and then let's try to find the other one. So the other one is on the right side of the screen. So when I'm being lazy, I usually tell my calculator to look between 0 and 10. If I was being more specific, 1, 2, 3, then I could tell my calculator to look between 3 and 4. My calculator will give me the right answer regardless. So if I do second trace, option number 2, I can tell my calculator to look between 0 and 10, ignore the guess, and it will give me the answer. Or I can tell my calculator to look between 3 and 4, and it will give me the answer. So both of those are good. I could tell my calculator to look between 1 and 5, it'll give me the answer. I could tell it to look between 2 and 7, it will give me the answer. I just have to give it 2 numbers that are on either side of where the answer should be. Okay? So the other x-intercept is 3.378, 0. All right. To find the y-intercept, we're still going to go back to that menu. We're going to do second trace, option number 1 this time. Second trace, option number 1. And to find the y-intercept, this option allows you to plug in any x value that you want. It just has to be within the window that you're looking at. So the default window on the calculators is from -10 to 10, so you can plug in any of those values. To find the y-intercept, we always just want to plug in 0. So second trace number 1, and then plug in 0. So 0, negative 6.586. Okay. Graphs are continuous if you can trace them with your finger without picking up your finger. I think the first time you learn the actual definition of continuity is in calculus. So you guys are closer to getting the actual definition, but for now this definition works fine. I can trace the entire U shape without picking up my finger, so this is a good continuous graph, and all quadratic functions are continuous. And then the end behavior, did you guys learn about end behavior in Math 3? Yes? So the end behavior is just describing the arrows. So basically we just have to, in a mathematical way, say the left arrow goes up, the right arrow goes up for this picture, or in this picture the left arrow goes down, the right arrow goes down. That's all that end behavior is. So for the left arrow, I'm going to say as x goes to negative infinity, that's left arrow. I'm going to say it goes up. So left arrow, x is negative infinity, it goes up. Y is positive infinity. For right arrow, I'm going to say x goes to positive infinity, and then y goes to positive infinity. So left arrow goes up, right arrow goes up. And the right arrow goes down. So we're going to start off the same way. So this is left arrow, this is right arrow. And what should we do to say that they both go down? Yeah, so we're going to say y goes to negative infinity, that means it goes down. Y goes to negative infinity, that means it goes down. So left, down, right, down.